Hello, everyone. Welcome back from the coffee break. We hope you are well caffeinated. I'm going to quickly introduce myself, and then I'm going to introduce the panel that we've got here. We're very excited for the panels we've got today, and this is one of the first that showcases a lot of talent we have from across Johns Hopkins University. My name is Olga Belaglova, and I am the director of the Emerging Technologies Initiative. I'm very much looking forward to working with all of you on all of the topics that we're going to be covering today. First off, at the beginning of the day today, we've got a panel on semiconductors, and we've got a moderator that I will introduce, and she will introduce the rest of the panel. Our moderator today is Mitra Taheri. She's the professor of in the Department of Materials Science and Engineering at the Whitting School of Engineering, and she is the director of the Materials Characterization and Processing Facility and a member of the Hopkins Extreme Materials Institute. Mitra, take it away.
Okay, thank you so much. Is this on, or you can hear me? Okay, great. All right, thanks everybody for joining. And so this is a really exciting panel, I think, as we start, especially, with all of our new investments in AI and where we've come, with respect to supply chain, AI, material science, critical materials. I think we're really thinking about how do we integrate policy into a lot of these grand challenges that we have today. So I'm extremely excited to share our thoughts and hear from not only our panel but also our audience, on what really is a new nexus of challenges here. We've had, as discussed in the fireside chat, with respect to semiconductor manufacturing, we have come to a point at which we're challenged by our limited manufacturing in the United States, but also our need, again, to rely on our global partners. And so really what we're hoping to discuss in the panel today with our experts is how we integrate not only geopolitical needs and an understanding of that landscape, but also how do we think about critical materials? How do we think about the way in which we approach design and integration of hardware and software, and really that need for the integration of AI and how we respond not only to the needs for manufacturing, but also to the needs for resilience in this current landscape that we're in. So we have this nexus of new challenges, especially considering AI with it being not only a solution, but also being a challenge in terms of large language models. Of course, we've all seen the effect of ChatGPT, and even the need for edge computing and 6G, and how we're going to realize how we're going to manufacture, control, understand, and really leverage our policy background in putting our arms around these grand challenges. So again, thank you for joining us, and this is going to be a really exciting panel. I have with me here on stage several experts from across the university. So I'll introduce first Andreas Andriu, who is a professor of electrical and computer engineering and an expert in particular in natural language processing as well as neuromorphic computing. Seated next to him is Ling Chen, who is an assistant professor at SAIS, working on political economy and state business relations. Melissa Griffith joins me also from SAIS, and she's a lecturer in national security and technology at SAIS, and she's kind enough to co-chair this panel with me and has really put together a great program today. Paulette Clancy is a professor and former head of the Department of Chemical and Biological Engineering, and works in computational modeling and integration of AI into computational modeling for machine learning. And last but not least, I have Mi-Yeon Oh, who's the director of Korea Studies at SAIS. So thank you so much for joining us today, and we're just going to kick this off. So I want to start with Andreas, and we talked a lot about the attention that we've paid to recently with the evolution of the chips that are made to date. And I thought it was really interesting, Lori bringing up this morning the types of manufacturing that we have in this country and what we're trying to build. The question is really, can you help us understand the importance of material science to the semiconductor conversation? And really, how are we actually managing not only building back up our ability to manufacture chips, but also the needs, again, like we discussed, for large language models and the next generation of computing, which, of course, you're an expert in.
Thank you. Thank you, Mitra. I hope I pronounced your name correct.
Yes.
I started first of all, my background is solid-state physics. And I started my career at a time where Teresinovsky of the neural networks frame was at Hopkins, and in the 90s were the big craze about neural networks, the first wave of neural networks and AI in machine learning and whatnot. And so at about that time, and then I'm going to get to the semiconductors in a second, the Hopkins did an article where my goal was to make a chip that would listen to you and really take your words, 1990, and transcribe them. Anyway, fast forward, we did create the Center for Language and Speech Processing, funded by the government at Hopkins. I created it. I wrote the proposal with a colleague that passed since then. And then over the last 15 years, I've been 20, 30 years, time goes fast, I've been working to really advance technology, integrated circuits to really solve problems in machine intelligence and perception, and machine perception. So now, let's go back to your question. I think 1974 was kind of a point where the first microprocessor was built by Intel, the 4004, for a register machine. And then we saw these advances in microcomputers. And then things went crazy, you know, exponentially growth. So materials is very important. I'm going to get to the materials, but I want to say something before going to the materials. We build machines by using machines and CAD tools, and CAD tools help us build better machines, and better machines help us have more sophisticated CAD tools. So what happened in the last 30 years, that cycle accelerated. So let's go and make some technology advances and materials advances in semiconductors did we see? Well, aside from the CAD tools, and we see technology evolving and scaling from when I started my career, 4 micron was the feature size. We made a chip in 4 micron. 4 micron is 25 times smaller than the human hair. That is the dimension of the device, think of that. Today, we are designing chips. We just tested a chip fabricated in 12 nanometer technology, which is 1,000 linear scaling, and 1,000 linear scaling is 1 million functional scaling, because in an area you have devices square of the linear scaling. So where semiconductors materials came in is to enable, number one, the scaling. And so that scaling means better dielectrics, better ways of fabricating the materials, and better conductors. You make things smaller, you make the wires smaller, but if you make the wires thinner, very thin, you cannot carry too much current in it, so they don't go fast. So IBM, for example, developed the copper damascene process that actually allows the chip not only to the transistors to become smaller, but to become faster. So then once you have faster wires, then you don't want the wires to interact with each other, so you have materials that actually are between the wires. And so at the end of the day, making the devices smaller is fantastic, and we have MOS transistor using quantum, operating at the quantum limit, so to speak, but it's everything else materials-wise that happen to enable those things to put together and make a system. And then moving on, well, going to things, chips don't just happen in air. They have to be packaged. They have to be put in packages. And dealing with the thermal properties of materials and whatnot, that's another whole issue that have to be solved. So in many ways, materials have played a huge role in making things that work that people can use, and not just a single device or a 2 device that you can write a Nature paper, publish it, and move on. Anyway,
yeah, Andreas, and I appreciate that, and I think that I'd like to hear from Paulette in terms of your opinion. You've been working in the semiconductor space for quite some time, and so how has AI enabled you and your colleagues and the field to really advance the needs for smaller packaging and design like that?
Yeah, thank you, Mitra. Can everybody hear me at the back? Yes, okay, thank you. So in my area, which is computation, I've seen a dramatic change since I started work, where the CAD tools that Andreas was talking about were really fairly primitive. Until now, where we finally are starting to encompass AI into semiconductor technology with real purpose, even putting them on the chip itself. And I noticed this even at conferences. 6, 7 years ago, I gave a talk about AI and materials discovery, and there were very few people who were working on it. Now, everybody at the MRS community is looking at AI, incorporating AI. So to get to Mitra's question, why is this important? Well, depending on the techniques in AI that you use, you have the ability to cut down the parameter space, which can be completely overwhelming. The choices that you have in selecting what components you use is very often overwhelming. And AI offers a real possibility to cut them down to a small number that experimentalists can test. So I think that's one big area, is sort of just down selecting from a very large field. But the other thing is the quality of the models themselves. We're now getting to modeling of the representation of the way that atoms interact at a quantum level, but yet doing it with sufficient speed that we can actually kind of make movies of what they're doing. That just wasn't possible a few years ago. So we're completely changing the landscape for materials discovery, for processability, and the latest thing that is really driving the field right now is automation. So I see those as the most important things.
Thanks, Paulette. And I think that, you brought up a good point, and many of us in the field that are, looking at AI accelerated discovery and design, we have this challenge of drinking from the fire hose, so to speak, with respect to elements. But, I think everyone else on stage is probably listening to us from the engineering perspective and saying, hello, we have other issues here. And the other issues really get to, I want to hear from Ling in particular in terms of when we're thinking about semiconductor policy, we're facing a lot of interactions with state issues, and that is going to deal with how we approach design. So AI might be able to allow us to tackle a vast space of composition and really, play with the periodic table, like we're playing with Legos, right? In a lot of ways, that's been what we've been enjoying, not really thinking about the policy. So Lynn, could you talk to us a little bit about, firm state dynamics, and in particular, how do we actually see how the business state relations in the U.S. and China and beyond really are shaping the way that we design semiconductors, and what constraints should we be considering that we can bring back to the engineering space as well?
Okay, thanks.
That was a lot of questions. So
yes, that's a lot of questions. I will see if I have answer for that. But yes, I definitely agree that state-business relations or firm-state relations are absolutely important for thinking about semiconductor policies, and that's the case for both U.S. and China. And they both face the challenges of how to intervene effectively in the industry, given that the semiconductor is pretty much the hardest industry to develop for any country, not just only for U.S. and China. But their challenges are different. So for the United States, for a long time, the National Security Council and other agencies sort of adopt a policy of U.S. primacy. That is, also they believe that United States can just keep running faster than China, and United States can just dominate the design of the semiconductors, and then business also benefit from relatively liberalizing order in terms of export control with China, because the business reap huge benefits by occupying the very top of the global value chain. But in recent years, such dynamic change as China emerged as the major challenger to the United States of overall economic power and out of geopolitical concerns, the government here, right? The government is the one that implement all these policies that started to weaponize global supply chains and started to cut off advanced chips from China. And that, though, does not change the fact that China is still the largest semiconductor markets in the world, which may go against the business interest of a lot of the companies in the United States. That's why we see a lot of circumventing strategies and all kinds of non-compliance issues or lobbying against from the business. So the challenge here, first of all, before we worry about the CHIPS Act, is for the U.S. government to have a broader and more comprehensive understanding of the entire supply chain of semiconductor supply chain in the entire globe, and to have a deeper understanding of how that affects the incentive of the business. But for of course, there's a lot of things to worry about the CHIPS Act. For example, how to gain skilled labor, not just like a normal any kind of labor, but skilled labor. They're highly skilled. They're required for chip manufacturing before. And then when you also worry about the reshoring of manufacturing, chip fabrication capability, and all those need to worry about. But I do believe that ultimately, probably U.S. has ability to solve these problems. So that the problem is not so much about the ability, but it's really about the incentives and how to align the incentives. Whereas in China, it's kind of the difficulties are kind of different because for a long time, China has this tradition of using industrial policies to push for industrial upgrading or technology progress. And the the start of U.S.-China tech war sort of helped align the state business incentives that now they both recognize that they were galvanized or they were forced to pursue self-sufficiency, to pursue advanced technology in chip design and manufacturing. But the problem for China, of course, the challenge for China is about ability because you cannot leapfrog, you cannot not have leap forward to something of an advanced cutting-edge technology overnight, and that takes really a long time to do. But China does have like a long-term experience of conducting industrial policy, whereas United States does not have a long-term tradition of doing that. And now United States is turning to industrial policies, so that is at a more detailed, firm level. So United States have to learn how to further align the state business incentives in the short term and the long term. Thank you.
So Ling, I thought that was really insightful, and what it really brings up is, to me, it seems that we're siloed in terms of the design space, the manufacturer space, and the use case space. And in a lot of ways, this has not been approached holistically. But I think, Melissa, you can really talk to that in terms of, the chips themselves with respect to manufacturing, and how further down in the supply chain, there are concerns with respect to China being, again, a large market, but yet the need to control the innovation space in China. And so, how are we actually dealing with that, and the national security issues around the entire supply chain, not only with chip manufacturing, but also, again, on this horizon of AI to 5 and 6G. So I think, if you could talk a little bit about resiliency and how we're going to deal with end-to-end supply chain, that would be great.
Yeah, no, thank you. So Mitra, I think one of the amazing things for everybody in the audience that may not quite grasp this, if you're maybe a little bit younger, is that it would have been very unusual 5 to 10 years ago to get this kind of diversity of expertise on a semiconductor panel, and to get this kind of interest from a diversity of students, including public policy, international affairs, governance students, which many of you are. And I think that speaks to the fact that this challenge is so multifaceted. It's a material science challenge, and there's questions in that space. It's a computer science challenge, an engineering challenge, and there's real questions in that space. It's a supply chain challenge and a market and a firm and state relationship set of questions, which Ling has touched on. It's about the national security priorities and the economic statecraft priorities, and it's about our relationships with other countries and the global politics. And all of those things are true at the same time in an ecosystem that is one of the most deeply interconnected, global, and complex. So that creates a wonderful stew for people trying to kind of play into this space professionally or in their studies. As I look at it from a national security perspective, so my work sits at the intersection between technology, national security, and economic policy, economic statecraft, I think there's really 4 issue areas that are animating the discussion in the United States, which is shared with some partners, but not all partners abroad. And the first, I think, really points to this conversation you've raised, Ling, which is I'm going to charitably refer to as the China problem, right? Which in, I think, the United States context is very much about civil-military fusion in the Chinese ecosystem. It's about indigenous innovation and a feeling around decoupling and strategic vision around decoupling within China in terms of developing their own ecosystems, of which semiconductors are one, and being able to leverage those much more broadly for civilian and military purposes at home, domestically, and abroad. And so there's those sets of questions, and that's very much where kind of if you think about the segments of the policy portfolio, things like export controls, inbound and outbound investment are really targeting, is thinking about that problem. But that's actually just one of 4 problems that the United States is trying to tackle consecutively, and they don't always align. Sometimes they're in conflict. The second of those problems is, if you have your kind of bingo card in front of you, prepare yourself for buzzword bingo, that would be resilience, and you can check that one off at this point. And so resilience and security of supply chains. And as we heard in our keynotes in the fireside chat earlier this morning, that's about diversity of players, diversity of geography, diversity of firms, alternatives, duplication, rules of 3. And that's a very different question than the China question and the China problem. Sometimes they overlap, but sometimes they're in conflict. So we have this resilient set of concerns. There's a third order set of concerns that I think is sometimes overshadowed by the China question and the resiliency question, and that's how do we think about chips as inputs into war and conflict? And so we see semiconductors at the forefront of our export controls and sanctions against Russia with the invasion of Ukraine, simply as a recognition, one, that you do want to have some consequences for invading other countries. So it's a bit of a kind of name, shame, wreak consequences effort, and also a recognition that chips play significant roles in the military enterprise. So that's kind of lane 3. And then lane 4, which is the conversation we try not to have but is definitely lurking, is about American competitiveness in this space. And where can we have American firms that can establish dominance and leadership and can be innovative in this space, and how do we make sure to maintain areas where we also have dominance and leadership? So you should be thinking from a policy perspective, that seems like a lot, and it is a lot. Those are 4 massive policy objectives that have very different toolkits at our disposal, from CFIUS to export controls, inbound, outbound investment, the CHIPS Act, how we think about labor, how we're thinking about investing in R&D and our material science, and we're trying to do all of that collectively at home in a very constructive, interconnected manner, and then do it with our allies and partners as well. So that is the policy challenge that faces us in this moment.
The discussion this morning of are we going to wall ourselves off, I think that really comes into play here, where if we're going to be competitive, it's impossible to wall ourselves off. And so I think, to that end, we really can't think myopically with respect to only the U.S. or the China problem, as you're saying. I think we have to have a broader global discussion and really think about who can we partner with to be competitive? Who are we partnering with now? What does that mean for the national security space as well as innovation space? And so, Mian, do you mind speaking, especially in the context of your role, about the dynamically evolving landscape in Asia Pacific, as well as thinking about the types of policy and wargaming challenges that they're facing at the moment in the context of semiconductors? Yeah.
Thank you, Mitra, and Melissa. Thank you for co-hosting this great session. So I would like to briefly share my experience right before coming to SAIS, where I joined recently. And I work at a think tank called the Atlantic Council and then running the Asia program. So I spend a lot of time working with Asian partners and including these major issues of the US-China tech rivalry and how we should work together with allies and partners. So Ling Chen and Melissa, she just lay about the policy dimensions, and I like to point out quickly that what we're seeing right now, we see major policy changes, especially into 2022. There were 2 October rules on export control in terms of the semiconductor, which Melissa just talked about, and what we're seeing is the law of extraterritorial, and also multiple FDPR, the foreign direct product rules, so specific technology going to specific destinations, etc. And at the fireside chat, we talk about CHIPS Act and IRA. Dean Steinberg talk about we are trying to build a high defense narrow yard. So what I would like to say is that I think we have, although the progress appears to be a little slow, but then clearly we have more clarity, and then actually more structured lines of policy effort, and actually led by United States. This is the unitary actions, and actually followed by allies and partners. And again, this morning, Jason, the CEO of the RAND Corporation, he talked about the importance of Japan and Netherlands to work with the United States on the equipment, semiconductor equipment. I also would like to talk about Jake Sullivan's National Security Advisor's Brookings speech in April 2022 this year, because I think it really shows very clearly the underlying assumptions about the economic security or economic statecraft, the Melissa, or the U.S. industrial policy that Lin Chan talked about. So the concept that the Biden administration wants to build up. And then what does it mean to is like-minded countries? And I mean, again, Dean Steinberg, I think one of his key questions about how far we can go, I think that was really the key question, and then has the policy implication, also not just foreign policy, but the economic policy for the like-minded countries. So what I would like to say is that I think still we don't have a coherent definition shared by the like-minded countries in terms of what type of technological ecosystem we want to build. And probably we have a little bit more clarity and coherence on semiconductor, it's more clear, but still I think it's very important to have shared understanding on this space. So we have the finer guardrails on semiconductors out of the CHIPS Act and IRA, and then so for instance, as a director of the Korea studies, I can say that South Korean companies like Samsung and SK Hynix, they have waivers. But what are their trying to do in the short term? The reason why I say this is in the Washington, D.C. policy community, from my multiple experience of working with outside partners, there's a shared understanding, I think, among the policymakers and think tankers that in the long term, this effort led by the United States on semiconductor is actually be beneficial to the countries and companies of South Korea and other like-minded countries. Yes, it is true, but we have to think about this is a very complex issue and with too many stakeholders in a very different level. So international versus domestic, government versus private sector, and interest group versus consumers. So I'm looking forward to hearing from other speakers as well, but that's what I like to say, and that's what we have to work with despite the domestic factors and moving forward. I'll stop here.
Thanks, Mian. This actually brings up, you brought up I think you called it a technological ecosystem. And I think when we think about the technological ecosystem, we've been talking about supply chains fairly loosely. We've been discussing, of course, statecraft and the challenges and opportunities of AI. What we're not talking about is that semiconductors are really at the heart of some of our more broader challenges with decarbonization, sustainability, and really energy policy overall, and our approach technologically. And for that, actually, we've had a hard enough time, from the technological standpoint of how do we reach our decarbonization goals, how do we reach our climate goals. that's a global issue that we've started to tackle. How do semiconductors come into play there? So how do we actually integrate not only the issues and challenges with the national security, but also the opportunities that semiconductors, and again, the beyond more computing, moving into that regime, and how that actually will be the answer to how we can reach our sustainability goals, and how we can move into a space that I think we can start to solve these broad challenges. So maybe, Melissa, I'd like to hear from you first, because I think we're excited about what that brings us, but again, that's an integrated challenge that I think is far beyond, in fact, the China issue and even Asia Pacific.
Yeah, I think at the root of this question, which is aptly put, is there's a tension in our policy, right? So when we're looking at these types of technology ecosystems, particularly foundational technology, of which chips or semiconductors, integrated circuits, choose your vernacular of choice, are, we're really concerned about their use cases. Right? So whether you're worried about the value they add, how they can be leveraged for economic prosperity and growth, or the decarbonization future, or national security, general purpose technologies, it's about the use cases. It's about green tech, it's about AI, it's about cloud computing, it's about 5G networks, it's about space applications, it's about 5G, 6G, it's military applications, it's about the application space. And rooted in that is a tension, which is how do we manage and mitigate the risks in this space as much as possible, which many of us have sort of alluded to, while still capitalizing on the benefits of that space as much as possible. And I think the green technology climate change component is the benefits of that space. And one of the challenges that we face is we have a very strong green future articulation, but the material science, the specific supply chain, the engineering to support that, to make that dream a reality, is not here yet. So there's an incredible opportunity, but I also think a call to action, not to sort of forget the benefit side of this industry, the economic and the environmental and the public health, right? The exploration, the benefit side of this puzzle, and continue to invest in R&D in these spaces, and the work that I know Paulette and yourself and Andreas all do, right? That can move us in terms of our policy ambitions that are currently being gatekept by our technological limitations.
Right, absolutely, and so part of that actually is really how are we interconnected with security and technology, obviously, globally, and so I'd like to hear from Ian again. Sorry to call on you right away, but really thinking about again, and this comes into play with our ability to invest in technology. So could you talk a little bit about the roadmap from a global point of view, in terms of like-minded countries investing in technology space to advance, again, our needs in semiconductors to respond to these global challenges, as well as having a consistent policy perhaps across those partners in terms of continuity of investment, continuity of economic security, and notably, how are the U.S. and the allies, that we hold close to us today, taking that into account as we move into election season?
Thank you, Mitra, and thank you so much for pointing out the policy consistency. So wherever I had opportunities to engage with business leaders from Asia, they all tend to say that actually this new paradigm or transition that we're watching in terms of the U.S. industrial policy or economic measures, it could create a great opportunity for market. But then what we're more concerned, we means business leader, they say that what we're more concerned is whether we would be able to have policy consistency. And for instance, there's a presidential election next year, and then how much continuity or discontinuity should we expect, with the result of the U.S. elections? So that's one point. And I briefly mentioned previously that there's a sort of the widely accepted understanding that it's going to be benefited the companies of Asians and like-minded countries in the long term. But then also it is important to think about short-term and mid-term in terms of the policy roadmap. Do we have a clear steps in terms of even short and medium term, and think about the situation where, like, I think this is a point when Lin Chen sort of alluded to. So let's say if one company decide to exit Chinese market, and then are they able to think about any financial intensive, because it would involve huge capital cost. So that's something that those companies from other countries are considering at the moment, and So again, going back to the coherent definition of economic statecraft, I like to just quickly mention the decoupling that Melissa mentioned, but what we are here a lot is de-risking. And then probably very surprisingly from the Asian countries, they are very curious about, is it a major shift from decoupling, and or if we want to emphasize more on the term of the de-risking, what does it mean, and then what are we trying to achieve, what is the end goal. So that's also very important. So maybe I can stop here, but then maybe really briefly, so I think there's a discussions on how this would result in the revenues in terms of revenues for the US companies, but then also it is very important to think about simultaneously for the revenues in the long term for the foreign companies.
Yeah, I think you bring up a good point, and I think there's 2 points that I want to touch on next. And many of us, obviously working in this field, we're thinking about again de-risking that landscape. So of course, if you take one player out, how does that change the tech to market goals? As we innovate, and how does that change the current revenue space and revenue stream, right? So in terms of the market. But what we also are destabilizing with these threats is workforce development, and I think we've already seen the effects of that, so greatly in policies on foreign nationals working in specific countries, policies on foreign nationals working, for example, in specific industries, and the inability to translate some of that highly trained workforce even across boundaries within the same company. And so I think that this is, we think a lot about supply chain with respect to the materials and the technology, but personnel and workforce is incredibly important, and I think that that's something that we have to think about in terms of that ecosystem and stability of that ecosystem itself. So Paulette, I'd like to hear from you, especially in within your experience, in terms of what is the strategic approach to self-sufficiency when we think in the context of semiconductors to educate and train students, especially in that context of tech to market, with respect to that workforce. So what are we doing moving forward? What's needed? And do you have any challenges that you'd like to discuss as well?
Thank you. I think this is an incredible problem, actually, because when you look at where students are headed, what are the drivers? I don't think semiconductor processing and enabling that is actually a very sort of sexy route right now. When you think of some of the competing ones like data science and AI, I can see the shift in my own students who formerly went to Intel and IBM and Applied Materials and so on, and are now going to data science companies. And I think what has changed a little bit is, and somebody brought this up, I think it was Ling, about incentives. So when I first started, there had been a major shift that the defense industries have been pouring in a lot of money into a class of materials that are called 3-5s. It's just a specific group of materials. But then other companies like Intel and IBM and so on wanted to create a workforce that knew something about silicon technology, which is the one that we're all most familiar with in the devices that we have. So what they did was that all of the industries got together and created an entity called the Semiconductor Research Corporation, which offered a lot of incentives for students to go into that area. And that has dwindled quite a bit in the interim. And I think that an incentive to bring people back to this area would be something that would be very helpful. The other thing that I think is important is that we train students without regard to sort of obviously where they're looking to go in the future. But I think that we could think beyond like the bachelor's level and look at some of the graduate levels and making this connection, a very deep connection between technology and policy and economics. We don't do a good job there, and I see that both as a challenge and a huge opportunity. So I think that it's incumbent on some of us, and I know that at Hopkins we're looking to think about that, is how can we marry those together and train people who have that old sort of NASA T, the depth in a field, but the breadth to understand the implications of the technology that they appreciate so well.
Thanks, Paulette. And I think I'd like to get feedback, going forward, not only from the panel but also from the audience in terms of the SRC, or Semiconductor Research Corporation, was mainly a technological consortium. Again, I think what we can think about is, as we build policy and as we move toward election season, are there coupled workforce programs that we can think about that would actually allow us to incentivize students, because we can't do anything if we can't actually work with them. So I think I'd like to sort of keep that little nugget in your head, audience, please. But Ling, maybe you could speak a little bit more to this as well, in terms of, as this US-China tech war continues, we've already seen kind of the implications with respect to, again, tech to market and workforce in weaponizing semiconductor supply chains, weaponizing critical and raw materials supply chains, in fact. And so what do you see as the future of this U.S.-China power competition in the context, again, of how we move beyond our current market, how we innovate, and how we actually train the future, again, for next-generation computing? How do you see that playing out?
Thanks. And well, so right now we're weaponizing the supply chains, and recently I published an article in International Security called "Wars Without Gun Smoke." Now, for people who are in international security or internet relations, their worry is about if there is a war with gun smoke. Where is Taiwan's TSMC going to relocate their manufacturing facility? That's what they ask the most. But I think in the short to midterm, I don't think this necessarily would. This kind of power competition and dynamics are not necessarily going to escalate into a real war or military conflicts, but it's likely to trigger sort of a what I call a vicious cycle, where the U.S. is trying to weaponize and the China is trying to pursue self-sufficiency and trying to pursue a high-tech, hardcore technology. Then they already emphasize a lot hardcore technology, which made them make more progress on that and force U.S. to weaponize even more. That kind of cycle, I don't see in the short to midterm it's going to stop anytime soon, partly because China is unlikely in the short term can catch up with the U.S. Technology level. But in the long run, we need to think about if there is one day that China did make progress and was able to reach competed with the United States with the power parity at the parity point, then what are the advantages that United States still have, right? Or is it because of the advantages in retaining talent, or still on the chip design, or how much capacity they have for chip fabrication? These are all good questions, because at the time, if the China's business are directly competing with the United States business, it's likely, the business, who worry about immediate commercial gains are sort of also on the same side with the government and wanted to contain China at the point, because they're directly competitors. But at that point, the United States may lose further weapons in terms of global supply chain when the Chinese side has made more progress. So these are all very complicated questions. What I'm saying is the United States need to think in the long term of, in the long term, not in the short term, but in the long term, what would be its strategies, maybe 20 years from now, and start to invest immediately now in order so that in the future, if there's one day that comes to the point that U.S. China are competing on more similar level, and what exactly is the future advantage like, if that's clear.
And I think so, and I see a lot of parallels. In fact, my background is actually in metallurgy, so I think a lot about, you know, our history, and we're sort of watching this unfold in terms of what is technology that is useful, what is technology that we're using right now, and where do we actually innovate? Like, did we need the old steel mills that we closed down? And the answer is, in a lot of ways, no. And so when we think about the U.S. and our ability to be competitive and our ability to innovate, a lot of that lies in the fact that we're now in the third wave of AI. So, you know, when we think about, we've all been watching obviously what's happening with OpenAI, but, you know, what became, you know, the explosion of large language models again, and next generation computing. Where do you see, Andreas, you know, the key advances in computing systems from both hardware and software points of view, and really, you know, how the U.S. in particular might be able to drive that beyond more regime? And so, you know, in keeping with the pace of the development and the use of AI/ML, again, when we think about that, will be actually the solution to the sustainability problem, right? But we can't get there until we innovate in that space. And I think that's an opportunity not only for the U.S., but also for our allies. And that allows us to not have to continue to rely on a stronghold in that, you know, in state relations, of course, as much as we can also invest in new innovation. So in light of the explosion of AI, as well as the explosion of you know, critical material limitations, can you talk a little bit about what our key advances are right now, Andreas, and where we're going?
Thank you, Mitra. First of all, let me answer the question that let me answer the question: what are we going to do with all the steel mills? Well,
I think we know, but yeah.
Well, the steel mills, we're not going to do much, but to have that steel mill, we have the power grid infrastructure,
Right.
And now we're turning the steel mills into data centers because the infrastructure is there to provide power. But now we're spending so much power, so future computing is not only about how many flops we're going to get or how many connections we're going to get to make these neural networks, but also about how to make them efficient. And we all in this room now have a very super efficient machine, and that's your brain, that the total metabolic resting costs about 15 watts, which is about a large LED lamp. So I think the innovation and the advances we see in AI is when people start thinking about building computers like the brain. Von Neumann wanted to do that and wrote a little book, the father of kind of the modern computer architecture, Computer and the Brain, but he didn't have the technology. So now, starting 1990, we're beginning to see design of computers that have the form, the function of the brain, which is parallel distributed processing with massively connected and whatnot. This is called today deep neural networks that drive everything that we do today. But going back to the semiconductors, it wasn't until we not only start looking at the function, but we look at the form of what the brain is all about. And the form of our brain, first of all, is 3D. You have layers of processing, and going back to power, the cost of information processing has to do with cost of computing and cost of commuting. So you have the bits that go and get computed, and you have the bits that they have to travel and commute to be computed. So I forget the cost of computing is roughly zero. Most of the energy cost in processing today is all about commuting, moving the bits around. And so instead of building computers like what countryside towns are distributed all over, we start building computers in 3D, like New York, where you have layers of chips passing the data very efficiently from one layer to another, and that is really what led to high bandwidth memory, what led to all the GPU, accelerated GPU that use 3D stacked DRAMs to actually accelerate moving the data from the processor to the memory and back and forth. Now, making 3D chips is all really a material science problem. How do you stack them? How do you make them reliable? How do you interconnect them? You have the chips. The chips are done. TSMC, Samsung makes them. Hynix makes them. How do you put them together? The packaging is material science. So going to that direction, then we see the emergence now of 3D technology that not only solves the efficient, which now looks like the brain, but now in form, not just in function. You know, we have begun these biomorphic, neuromorphic systems that have the form of the brain and can address both the requirements for processing and also the metabolic, the energy cost requirements, and have energy efficient computing. And I will finish by just saying, 30 years ago, I started my career by wanting to build a chip that could listen to me and obey. Today, as of about
discuss this.
Huh?
I'm
Well, I
teasing.
mean, yeah, I mean, the chip, I want the chip to obey, yes. Like a Roomba, go and
right.
clean your house, you know? Today, we have a chip, that was the article, actually, there's an article about that. Today, we do have a chip, and I can tell the chip, hey, build a chip to make yourself faster. And here comes a chip that can be fabricated that will accelerate, a neural network chip that will accelerate ChatGPT and whatnot. And that's reality, which is amazing.
Right. So I think, Andreas, I want to close by getting everybody's opinion on that. So now that we're moving into, truly autonomous systems, right? So we now have utilized semiconductors and AI in concert to have real-time decision making, and that that could be on a factory floor, that could be in a missile head, that could be in a lot of places where we need to understand again the role of policy and the role of how we actually have again not only a stable but an umbrella approach within allied nations. And I think that what edge computing is doing for us is enabling communication, enabling again human brain level decision-making processes, like not only obeying but also making its own decisions, which becomes a challenge. And so I guess I'd like to start with you, Mian, in terms of what is the global outlook, especially in the context of integrated industry to edge computing and 6G, and how we think about communicating devices and decision-making devices, and how that's going to play a role in policy?
Thank you, and there is a very tough question. And so as a person who work, years of experience in the policy community think tank, I actually wanted to have reactions to what Lin Chen said, and then also responding to your question. So I completely agree with what Lin Chen said in terms of, do we have a long-term strategy or vision? I think we do, and then I think it's pretty clear what type of new norms and paradigm that we are trying to build on right now. But then it should be supported by policy. That's why we talk about policy consistency. And then what we have to think a little more, and then we haven't really touched upon on this panel, is probably the critical minerals. Mm-hmm. So the export control that we talk about on semiconductor is where United States has leverage. That's why US imposed export ban. But then likewise, China has leverage in terms of the critical minerals mining and production. That's why they have export ban. So not just in the realm of the US-China competition that has deep implication for allies and partners. So I think I just wanted to pose the question for taking full consideration, and then maybe I can just stop here.
Absolutely, yeah. Paulette, do you have any comments on this?
Yeah, I want to tie together the topics of advancing the speed and performance of our chips to green considerations, environmental concerns, and policy. So silicon, the material that fires up most of our chips right now, comes from rock. So making rock into a beautiful crystal takes a lot of energy. There are other ways of actually making semiconductors that are also very efficient, but the problem is that sometimes they are based, for example, with lead as one of the key components. And then you run into a policy concern that places like Germany have banned lead. It doesn't matter how rational that is in terms of how much lead you actually have. But once you have that, then you're forced back to sort of innovate again with what is a suitable replacement for lead. Or perhaps in a more enlightened state, maybe we could look at how much, and talking about de-risking, how much are you willing to risk for a much greener product? How do you balance that risk? So I think that there's this natural tension between wanting performance, wanting it green, wanting it to fit in with policy and commerce. All of those things come together, and at some point there's a pain point.
I agree, and I think what we would love to realize is a future of critically lean manufacturing, right? Because what that does is de-risk and innovate, right? So I agree with you completely. Melissa, what are your comments in this space?
But I will contain myself. Yes, I think there's a couple things. Building off, I think this conversation we've been percolating around green tech that we haven't mentioned is the semiconductor industry itself faces environmental challenges in terms of making it a more lean process and considering kind of the electricity and the water consumption that goes into that. I think this conversation about what will be the edge compute, the application space that we see in the future, as someone sitting on the social science side of that equation, I would caution us to say that there is a distinction between what is technologically possible and what becomes a business interest and something that is market viable and something that is consistent with and applicable with policy. And those three things have to come together for us to realize the future that we're talking about. So it's not enough, it is necessary but not sufficient to have the technological component there. There also needs to be the business case, which is as much about kind of return on investment, time to market, and stability of the ecosystem they think they're engaging in. A lot of these businesses are making 10-year bets, and when policy life cycles are quite disruptive, it's very difficult to realize return on investment and to want to be on the cutting edge of that application. So I think recognizing that kind of confluence of events. And I think the last thing that I would emphasize here, that's something I think I see a lot in the policy conversation, is people want this moment to be costless. Right? That we can have our cake and we can eat it too. We'll solve all four of these problems and our businesses will thrive and no one will suffer any economic revenue losses and our industry will be as innovative and competitive as ever. And yes, you will be able to get the smartphone when you want it and your Game Boy on your table. We won't suffer any consequences or negative components. And I think the reality is we will. Right? Like this is about managing loss and managing risk and doing that in the least painful way possible, but recognizing that the metric for success cannot be zero pain. It has to be sort of tactical pain, and then how do you compensate for that in terms of creating other opportunities?
Absolutely. And Ling, on the subject of pain, in terms of global relations, do you have any comments on that?
Well, I guess we already have enough pain, so
Yeah.
I don't have to add. But I would say, because previously I talk a lot about U.S.-China relations. Of course, as Mia and others have all mentioned, it's not just only a U.S.-China problem. It's a global problem. There's a lot of countries, and for each country, there's always the state and business side. And if you see, like for example, in South Korea, how those business lobbies for something that's different from what the government wants in terms of their relationship with the United States, right? So so I don't want to add more pain. Let me just stop there.
Thank you. Andreas, any forward-thinking comments on how we have a holistic approach here?
I'm just going to comment on something that I said earlier, the obeying. I was talking in terms of, we all have pets. You have a dog, and you train your dog to obey, to sit. And so my students actually were making fun of me because when we were using ChatGPT, I will ask every prompt, could you please do this for me? And they were saying, what are you talking about? Why are you? So I didn't use the obey in a training sense. But no, I think I've talked enough.
So I think I'm doing it all wrong with my children, then, is what you're saying. So, well, I want to thank our panelists again, and I'd like to get some feedback from the audience if there are questions from the audience for our wonderful panel. Thank you so much. It's been a great discussion, and as you can see, we have a lot of problems that are unsolved and a lot of interesting issues. So, do we have microphones in the audience? Okay, wonderful. So, can I invite anybody to ask us questions, please?
So
Yeah.
I'm going to start. if I
Thank you,
can.
Dean
Thank you
Steinberg.
all. This was fantastic. I want to ask a question coming off Andreas' observations about biomorphic computing and biomorphic chips. I want to, at a risk of oversimplification, you all know this better than I do. In some ways, if we look at the evolution of the space, we see a kind of movement where, for a while, the sort of the tremendous innovation was on the hardware side. You know, we developed silicon, we developed chips, we developed microprocessors, GPUs, and things. And then we got to a point where everybody said, oh, well, actually now we're going to do all the innovation on the software side. And that you know, we don't, and one of the consequences of that was manufacturing became much less important. If you're just doing software, you don't need a lot of machines and stuff like that. And now it feels like it's kind of the pendulum swung back, and now it's all about EUV and you know, and 2 nano chips and things like that. But what intrigues me about Andreas' observation about biomorphic computing, biomorphic chips is, are we overseeing the hardware side? And because our whole strategy now is about hardware control, controlling machines, controlling all these things. And or are we at kind of at the end of sort of the Moore's law of the physical side of this, where it's now thinking about different things? And what would that mean for policy if, in fact, we're controlling the machines, the ASML machines, the materials that go into it aren't it? But you all know better. I mean, where is the innovation going to happen? And if we were thinking forward-leaning and trying to anticipate the policy, how should we orient the policy not to the current state of where the technology is, but like what the next generation would be?
I'm going to try to steer the panel here. I think the use case really drives the hardware innovation, and so that's where you know, earlier this morning quantum came up, and part of the reason we haven't sort of realized the goals of quantum, you know, are that algorithm development and materials development have not been done in concert. And I think that Andreas can talk about this really, you know, elegantly in terms of co-design of hardware and software. And that's something that, you know, the gaming community has actually taught us this. So the gaming community was like, you know, using old hardware is not enough for the gamers of today. And in fact, actually, that was NVIDIA's market, right? So, you know, when you think about it, so now with our development of AI, the reason we've reached a Moore limit is because you're right, that we simply didn't design the hardware to manage the decision processes that we're making and the data processes that are required. So I think I'd like to give that one to Andreas and then think about what that technology policy looks like, again, for companies like NVIDIA and beyond. So go ahead.
No, I mean, I think that is a very insightful comment and suggestion to comment on, and that is, I think we're moving away. We're going to have machines that are going to recognize cats and dogs and characters and ChatGPT. But at the end of the day, the AI revolution is going to come when we have machines interacting with humans beyond the Roomba and doing things that we don't want to do. And how do you regulate? We're going to have machines that are going to tell you, well, today is Sunday, I don't work on Sunday, you know? How do you deal with that? And to do that, you cannot do processing in the cloud. It has to be local, it has to be timely, it has to be with low latency. 5 milliseconds, 6 milliseconds is really what the humans can accept to interact with the machine, you know? You give them 10, 20 milliseconds, you lost the human, you didn't lose the machine. So I think this is really co-design, as Mitra says, is the name of the game. And also, we're moving away from the limiting case being the design, when I design an accelerator chip in 2 weeks using ChatGPT, to manufacturing. How do I manufacture that chip in 1 day, in 2 days, in 3 days, in 1 week?
Well, I think that gets into, you know, what does the panel see as the challenges in manufacturing, especially when it comes to policy? So if we are going to build, you know, an allied approach, you know, to low latency computing, right, which is really what we need, how does that happen beyond the U.S. borders? Beyond Melissa, Ling, any comments?
We're all looking at who's hot potato.
Yeah.
So I think a couple things that are embedded in this comment that are really astute is, where does performance gains come from? Where do performance gains come from? And historically, we thought it was like a rat race to smaller and smaller and smaller on the hardware components. And what we're seeing is greater investment in packaging and in architectures, and that's a very different R&D life cycle. If you're sort of thinking about the replicative process of go smaller, it's like, how do we get better performance? Smaller. How do we get better performance? Smaller. And now we're getting these sort of one-off sets, right? Packaging innovations or innovations on the actual architecture, the software of the chip. Believe it or not, there is software on your hardware. And those are kind of almost one-off, right? You spend them, and then you need to go back to your R&D department and figure out what the next iteration is to get performance gains. And that's a different capital investment for our design firms. So I would sort of point to, we're looking at different moments in the market to intervene. I think it also tells us something about, Dean Steinberg, where we should be looking as we are concerned about the future, right, of our ecosystem. So not just regulating or approaching the semiconductor supply chains of today, but the ones of tomorrow. And I think there's a lot of conversation, and rightly so, on focusing on where packaging is occurring. Because if we think in those three axes that packaging takes a far more significant role for productivity gain, that's a much more value-add component. This was traditionally, back in manufacturing, considered to be capital or labor intensive and not as interesting or sexy for a lot of markets, and we've pushed a lot of those, right? And we need to be really thinking about bringing those back into the space. And I think the third trend line that we need to be understanding on the policy side is a very industry specific, and it's the shift from kind of the specialization across the supply chain where you had manufacturing companies and design companies and use cases, user companies, to the users themselves getting involved in the design with a direct handshake with their production in the hardware, which is, I think, what Andreas is also pointing to. And that's sort of like the Apple components, where you get a whole bunch of entrants, Apple, Tesla, and others, into the design process because they know exactly what application they want to use this for. They want to specify for a specific application. They want the design process, the manufacturing process, and the hardware and software to have a very tight handshake versus chasing to the smallest component as a more general purpose application. So we're seeing a real shift in what we are actually trying to intervene on as a market.
Absolutely. Thank you, Melissa. And then I want to take some questions from the audience.
To add to what you said, the term that is used today is chiplets. We're designing systems using modular components, which are called chiplets, that rely on very sophisticated assembly, packaging, to really get the functionality that you have, like the Apple Ultramax. It's an amazing manufacturing packaging device. You know, I mean, it's really insane what you have there. So.
Exactly, the opportunities. Well, thank you guys. And so why don't we go from this gentleman right here, please?
Yeah, so my big question goes back to introducing new people into semiconductors, like students, like we were talking about how students are into the really cool data science, machine learning, and what I see in the industry is that people only need an undergraduate or a master's degree to start in that market. And from this conversation that I've heard, it sounds like you need like really advanced education to break into this market, to really start innovating on semiconductors. So my question is, can we lower that barrier to entry? How would we go about doing that? Because I think that that's a big reason why younger people aren't going there, aren't doing it.
Paula, would you like to comment on that?
Yeah, I think that's a fascinating question, actually, because we have a very entrenched view of what an advanced, like a PhD degree would have and how that comes about. And that doesn't necessarily help with the problem that you're seeing. So what could we do? One of the things that we could do is, and actually something that some universities, including Hopkins, is sort of getting their toe in the water, is what they call a Doctor of Engineering degree. And I'm not sure that it's exactly the right vehicle, but of using somebody's placement in industry and essentially linking them with academics so that they can stay embedded in their industry and yet get the sort of innovation and get to that real cutting edge and get to the sort of self-sufficiency that places like Intel and IBM have always really required a PhD for innovation. But maybe we can start, that's one idea, is to just use a sort of an embedding. But the second idea is to say, to do almost like a lean degree in what exactly are the skills that you need to teach somebody to be an innovator. And I don't think that you necessarily, I know this is a little heretical to suggest, but you don't necessarily have to do the traditional route in order to be an innovator. And I'm seeing this with the Hopkins undergraduates are amazing. And I see people there who they're acting with the AI skill sets, for example, of somebody who's already in graduate school. Why don't we try and harness that a little bit better than we're doing right now? But that would take real innovation in academia, and academia is not known to move tremendously fast.
Tremendous is an overstatement? Yeah, no, that's true. And I think tracked programs and integrated programs with industry would help. I'm going to switch back and forth with sides, so please stay there. Yes,
we also need people that have jobs and work, and I think perhaps we can look at a different model, maybe the German model of a technical training, where we can actually train people to do semiconductor process. Yes.
Exactly.
Yeah.
Please,
hi.
ma'am.
Thank you. So my name is Elizabeth McBride. I'm a student here at SAIS. So my question's going back to the rare earth minerals and China's leverage in this area. And because I've been following companies that are looking out west for rare earth minerals here in the U.S. And there's also an emerging conversation, I think, in the tribal nations about how much is on their land or near their land. And I'm just wondering where the home for this policy conversation, which is going to be so complex, is in Washington. Are people talking about it? Are people aware of it enough yet?
I think they're aware of it, for
Yeah.
sure. We had a program manager from DARPA come and talk to us about the fact that right now, all these things come from rock, again, lithium and all the other what they call princess materials, metals especially. So it's on everybody's radar. And I think, honestly, this brings up a question that we haven't even touched on so far, and that is sort of social justice and equity. And so we're very used to, if you think about energy supplies, when it was wood, most people had access to it. Once it became oil-based, there were a few countries who were dominating it. And then once natural gas came out, a few more could join into the game. But we're leaving out a tremendous amount. For example, in the African continent, I think it's something like by 2050, 1 in 5 people in the earth is going to be from Africa. We're not engaging with them. They don't have energy equity, and they're not the only ones. So I think that we've talked about policy and so on, but I'd really like us to talk about social justice, because if you think about, lithium, for example, where is it? Again, it's very concentrated in certain areas, and then that leads to issues like the whole sort of adversarial walls that we put up in terms of export controls and so on.
Well, and I think you're right. And we've been talking about weaponizing, the rare earth minerals, which we already have seen, right? So please comment on this. Yeah.
Thank you. So just quickly, so there's a critical minerals partnership led by the United States where allies and partners are already committed to say that they're committed to, basically participate and cooperate. And you are correct that this is not really rare earths, but then it's actually abundant. But then it's a matter of the environmental degradation. And you might want to take Japan as an example, where they actually were one of the forerunners in terms of their diversification strategy. So in 2011, Japan and China, they had dispute over territory, and then China imposed the export ban in terms of the rare earths. So since then, Japan was trying to look for other markets to reduce their dependence on China. So rather than looking at this is through a lens of U.S.-China rivalry, but then just trying to look for a diversification strategy. So there's a lines of effort already internationally, and then so there's a, very aware and quickly. So there's a Linux Australian company, also very big, production and mining. So they won the DoD actually the project, and then so the Linux was able to enter the U.S. market for like decades, more than maybe 20 years within. So because of this new lines of effort, it is actually happening.
Andreas? Yeah.
I have a comment on this business of mining. Mining is a tricky business in a federated. We are a federal government, and you have states. So you could mine in Colorado, and it could affect Colorado River down the stream 4 or 5 states later, or 3 states later. And there's an example of this. Paradox Valley is between Utah and Norwood. Used to be where a lot of the mines for the nuclear reserves came out. And even though the people there want to open up the mines, the states downstream, they don't want the mines there. So you have policy that not only is a federal policy, but now you have to deal with the states. And that becomes very, very, as we all know with the water rights, complicated at the state, at that level. So I think it's a bit more complicated.
Yeah, and I think just to close, from the material science point of view, the Department of Defense, Commerce as well, and DOE are all thinking about solutions at the university level, at the industry-based level, to really come up with ways not only to manage the supply itself, so access to the supply, but also resilience through recycling, resilience through forecasting, resilience through AI-enabled technologies. And so I think that's where the innovation is really going to come about, because it's not necessarily about access or even equity. It's also about how do we move beyond that completely. So I think that's something that this is coming about from the materials community, and we've seen this before. And so I think that this is something that we'll be able to manage. So thank you so much for your question. You start, would you?
I'm old enough to remember when magnetic core was struggling and bipolar was dominant. And so most of my professional career was watching the rise of CMOS, and that was a struggle. It wasn't a natural process. There was a lot of smart people who made CMOS work and gave it the place where it is right now. As I look at the applications that people are talking about right now, and this relates to what you were saying, I have the feeling that people at NVIDIA are really flogging CMOS. And that for what we want to do right now, we want to go, a phrase that has occupied the profession for the last 20 years is what's beyond CMOS.
Yeah.
How do we go beyond CMOS? Because it has some huge limitations. Are we investing enough in looking for what's beyond CMOS? Because sometimes CMOS has been 50 years. It's an old technology now. Yeah. We've done all sorts of wonderful things with FinFETs and stuff like that, but that's still CMOS. So are we making the investment to go beyond it?
Andreas, yeah.
It relates to materials. Yes. However, let me start saying CMOS is here, and it's going to be here, and it's not going to go away. So what is CMOS plus? What do we add to CMOS? Magnetic. So the biggest challenge today is really introducing, again, going back to the brain, form and function, form. Putting processing where memory is, or putting memory where processing is, near to each other. And to do that with new materials. And one class, my favorite class of materials is ferroelectrics, where you can actually store the information as a polarization of the material and control that and read in analog and do continuous and do multi-state and energy efficient. So do we do that in this country? No. In fact, if you want to get a CMOS chip with ferroelectric, you either have to go 12 nanometer TSMC if TSMC allows you to do that, or you have to go to Global Foundries in Germany, Dresden, that do that, again, outside the United States. So that is a capability we need to bring in the United States, adding functionality to CMOS. Yes, thank you for the question.
One final comment. I'm old enough to remember as late as 1990, people at IBM saying that bipolar was going to be around forever. And it is still around, but in very niche applications.
It is. It
So
is.
I would question whether CMOS where
Yes.
it will be in 20 years.
Well, we'll see.
Thank you. Did we have another question behind him?
Hi there, my name is Eric Hadland. I'm with the Semiconductor Industry Association. On this question of recyclability, materials, I think there are political solutions to these, and those can be defined maybe over shorter timeframes, but it's really important for us to maintain that these can also be science problems. So if you
They
take
are
a look
science
at,
problems, right?
if you, right, and it's important that we, engage them as both. So that we can manage our short-term risks, but then also create long-term solutions. So for instance, if you take a look at like a physical vapor deposition system that uses some kind of precious material, most of that material is actually coating a chamber, and then we need to use some god-awful chemical in order to remove it, which is creating environmental problems, right? If we invest in additive manufacturing technologies, direct write technologies,
Right.
we solve an environmental problem between Colorado and California, say, and we also solve a mining problem and getting precious materials from parts of the world that we really not like to get those materials from. So science problems, treating these as, I'd rather solve them as such, in spite of the fact that it's probably a both and I'm wondering if we need to put a little bit more emphasis on that.
So I think I can take that one, and then I'll let that. So I would say that at the forefront of what we're doing as material scientists, especially when it comes to the context of AI and autonomy, is closed loop approaches. And so you've seen this with respect to physical vapor deposition, additive manufacturing, direct write, and also biological printing and functionality. And so this is an all-encompassing problem because our ability to have precision manufacturing so that we don't coat chambers, so we don't have iterative manufacturing, it actually lies in our ability to make decisions during the process and how it's happening. And so how do we do that? We use semiconductors with on-chip decision, and we get all the way back to the beyond more computing. So this is a very much, not only is it a closed loop in the manufacturing process, it's a closed loop in how do we respond with the innovation in semiconducting technology. So I would say I'm actually proud to say that at JHU we're on the forefront of this. So we're actually, pioneering closed loop approaches in additive, not only for, functional materials, but also for structural systems. And actually, I think somewhere in the audience, there's colleagues of ours from PNNL. We're also running centers to do that, to respond. This is early stages. It's early stages everywhere. You see at Berkeley, there's centers. We actually learn a lot from our colleagues in Canada. There's the Acceleration Consortium, which is working across pharmaceutical and chemical industries, as well as kind of moving a little bit into hard materials. So, and again, and beyond, there's, the Ernst Ruska Institute is actually responding to this a little bit as well in Germany. So there's many approaches to closed loop, but we're not there yet because inherent to it, as you know, are issues in semiconductor innovation and even CMOS for that matter. So Andreas, please go ahead. Yeah.
I'm going to talk about education. I teach microfab, and for the last 30 years, we have a very simple clean room. At the end of the semester, right now, in the fall, the students have to go and look at the environmental impact of what it costed environmentally to build the chip. It's a microfluidic chip. How many watts of energy, how much material, how much waste. And when they are done with their chip, which is about that big piece of glass, they are amazed how much energy they spend, how much waste they produce to make a chip. So training and education and making people aware about it is also part of our job.
Absolutely.
And also, I'll also add that chiplets are an important part of this because right now when something goes bad on your phone, you throw out the whole package. In a chiplet solution, you get to pick out the part that's bad and maybe replace it with something else. The other thing that I wanted to raise was on the workforce development discussion. And you're right that it's hard to get people to go into the semiconductor industry for many reasons. Chief among them is we're kind of an invisible industry. We serve B2B customers rather than direct to consumer, as opposed to like a Google, which everyone uses every single day. And one of the ways that I think we can connect with the next generation of workers is by casting semiconductor evolution and innovation as a climate change mitigation strategy. That's something that they care a lot about, and there are a bazillion applications and use cases for semiconductors in green tech. It's up to us in the industry and up to us who study this to help make those connections to leverage and tap into the drives that actually our next generation students really care about.
Okay. I think Paulette and Melissa, you have comments on this, but thank you, Eric. They're wonderful suggestions. Go.
Yes, mostly just to amplify and thank Eric for trekking down the stairs to make that point. I think there's often when we talk about the policy space, it's sort of how do we help industry do things that industry didn't want to do for the betterment of society and national security, right? It's sort of like they're at odds with each other. And there's a whole suite of policy levers that are about enabling industry and enabling innovation in a much more effective, quicker, lower cost manner, right? And so I think there's a vibrant discussion, and we should really amplify it, on how do we invest into the work of my colleagues up here on the stage that are doing engineering work and material science work? How do we reduce barriers of entry into market? How do we help them with capital investment, which is all about, can we make the technology do more for us versus see the technology as something that we need to kind of constrain and wall off and as a scary thing we're trying to intervene on and control. So thank you so much for that interjection.
And Paulette, you had some comments on this as well.
Yeah, I just want to also comment on that. I would love to see a closer industry, academic interaction that would show people where those problems are. But I think there's an image problem. It's a bit like, in fact, my own discipline, chemical engineering, has an image problem because they see us as big oil, big pharma, things that they love to hate. But chemical engineers are driving solutions for a better world. I think that also the semiconductor industry, you're right, it's invisible, but maybe we can make it more visible by really starting up some kind of cooperation where students feel like they're going to really, truly be engaged in helping to make things greener.
Absolutely. But if we make you the villain, then everybody comes to material science. One last question, please.
I'm kind of curious in terms of fabs. How do we create fabs quicker? How do we build them? How do we build more of them? Because more specifically, I mean, as you all well know, TSMC is just really wants fabs, and whether it's Arizona, whether it's Colorado, pick your state. I mean, they want more, but at the same time, it takes a long time to build them. In addition, I guess a secondary question is the R&D tax credit. How do we create more of an incentive to get policymakers to say, "Hey, let's do something. Let's put more money from a government perspective into R&D." How do we create that space as well?
Well, I think this is a great question, and I think actually we also need to ask the question, how do we create the right fabs? And so we saw a lot of investment, for example, in honestly old technology. So you see the Intel fab that's going up in like Dublin, Ohio, is going to create, I think, 3,000 jobs, maybe 3,000 jobs at the very most. But it's extremely old technology, even as told by Intel. This is something that's a stopgap measure. And so I think the question is, how do we fill those near-term stopgaps? But the real question is, what does the next generation fab look like, and how can we efficiently do that? And is it a modular? Is it a partnership of large and small companies? What does that look like? And so I think, Andreas, you probably know the most about it, and Paulette. So please do contribute.
Oh, I was just going to, if there's any Star Trek lovers out there in the audience, my immediate thought on your question was the whole Kobayashi Maru scenario. Mm-hmm. So this was an unwinnable exercise for cadets, right, in the Space Academy. And what Captain Kirk did was to reformulate. I think he actually hacked into the computer and changed it. But that aside, he reformulated the question. And I just want to double down on what Mitra was saying. It's not, the fabs are so costly, but if we rethink them, that's the answer, really.
That's exactly right.
And along the same lines, let's not throw things away. Let's make them fabs for certain things that require certain processing, and so let's be efficient, let's be modular. I think that can be done, and I think it's been done now in some capacity, but we need more. I mean, I think that's really what it is.
And I think to me, it looks like, your large companies are not able to innovate as rapidly without pain, to put it in your terms, Melissa. And I think that's where we think about what are the partnerships from university to private equity to et cetera. And I think that's where we're really thinking about, like, what is the rapid innovation piece and the opportunity there? And that's where that modular fab tech can really come in, and that will answer our sustainability problem. How do we modularize our recycling problem? You know, does it have, you know, can we do this end to end? Can we bring that to the fab site as well? And so I think there's a lot of opportunities in green tech as well as more innovative, you know, next generation computing as well. So if there are no other questions, I think what I'd like to do now is thank our wonderful panel and thank all of you in the audience for sticking around. And I think there's a lot of problems that we can talk about. So hopefully throughout the day we'll be able to mingle. But once again, thank you so much for coming, and thanks for joining us here at our wonderful new building. And to the panel, I had a lot of fun. I hope you did too. So thank you.
Someone that can bring Mitra in contact with a fab would love to do that.